physicist. I'm engineer, working first years of my career in the nuclear power plant. And only after that coming to the science and positron annihilation, and this topic I will summarize according to my experiences. Good. In the last 5 years, I tried to improve our institute. We created institute. I was director of the institute. I was responsible to take these techniques, and based on the previous experiences and activities, you can see what our Institute of Nuclear and Physical Engineering can use in the study of the nuclear materials. We are focused on the operation of the nuclear power plants in Slovakia. Perhaps people in China could ask me, what does it mean Slovakia? It's state. We are very, very similar like Wuhan, but our agriculture is perhaps better. Good. It's the team of the people doing this research. Not everyone is doing positron annihilation. There are people doing atomic force microscopy and mass spectroscopy and XRD as well. But you can recognize some young colleagues doing also positrons. Good. Motivation was perhaps the second one, new knowledge for understanding of neutron embrittlement in the materials for nuclear power plant. That's the topic of my presentation. Let's start to speak about the technical point of view to the problem. Problem is neutron embrittlement of the reactor pressure vessel. And if you consider to build new nuclear power plant, you need approximately 8 till 10 billion US dollars. Reactor pressure vessel is approximately 8%. So if you have 700, 800 million, you can make this reactor pressure vessel. This one is for the Olkiluoto nuclear power plant. It's the largest one, 1,750 megawatts, which is currently built in the Finland. And this one we have in the PDR facility, also in Slovakia, in Bohunica, Mochovce nuclear power plant. It's a big difference in the diameter. It's the crucial to know this cross-section diameter is 3.6 meter, and this one is more than 6 meter. What does it mean? Because of the transport. This is 215 tons. This one is 560 tons. It's so enormous that it's very difficult to transport, and therefore this nuclear power plant have the trouble with the neutron flux from the core to the wall. And that's crucial for the embrittlement, and that's crucial for the lifetime. Actually, people are thinking from the end. Finally, we have made decommissioning. And the cost for decommissioning of this steel, because it's active, there's a lot of cobalt-60, it's also on the level 300 or 400 million of dollars. So to know the structure costs a lot of money. Mr. Nagai said yesterday that the lifetime is limited on 40, actually on 60 years, but each utility try to prolongate the lifetime. And it's necessary to prove that the reactor pressure vessel is okay. How we can prove it? Only to study the specimens, original specimens taken from the reactor pressure vessel. But if you take it from the wall, you cannot operate because it's damaged. So therefore, several specimens are put into reactor, irradiated, and the study is performed on these several specimens. Good. Next, what you do is annealing. Not put it into the oven, but the oven bring inside of the reactor pressure vessel. It's like spiral. You put it inside 10 centimeters from the wall, and you can make annealing. So, study by positron annihilation of the sovereign specimen is necessary to do in the time temperature regime, which is done for many years already. Aging. We have actually more than 430 reactors in the world in operation, but 50% of them are older than 30 years. If we will not prolong the lifetime, it will be shut down. There are many effects from irradiation, how to study or how to know about the changes of the irradiation. We will focus, and we focus mostly on the neutron knockout atoms from the lattice, because gamma radiation, electron radiation, and other types cause small changes, but not such large defects, because what is studying? Studying is embrittlement. Embrittlement is creation of the defects, which are mostly moving to the dislocation, to some boundaries, which makes obstacle against the plastic deformation of the material. So therefore, this knockout atoms is the crucial for from the mechanical point of view for the embrittlement. So I mentioned that chemical composition is very important, and when we speak about decommissioning, we need to know when we can cut this reactor pressure vessel, and it depends on cobalt-60 inside. And therefore new materials are developed mostly therefore to access the reactor pressure vessel in the later. So neutron irradiation caused different type of the defects which can be observed also by the positron annihilation. It's also well known which defects are caused by the irradiation, and perhaps we can consider which these defects we can observe and how we can identify these defects. There are many non-destructive techniques for application. Positron annihilation is one of them. But this positron annihilation technique proved in the last 20-30 years the real benefit in the study. There are not many techniques which could be compared with the destructive mechanical tests. What is crucial for the Nuclear Regulatory Authority by evaluation if the reactor pressure vessel can be operated in the future or not? RPV test and tensile notch test. So it's necessary to correlate positron annihilation or other techniques to this RPV test or tensile notch. I speak a lot with the people from the industry, and they do not want to speak about physics because they do not understand it too much. And after this discussion, I made this picture, which is the user's approach to the positron annihilation. And I wrote some report from the European Commission some years ago, about 100 pages, what kind of information we can obtain from positron annihilation spectroscopy useful for the industry. So somebody would like to know defect density. Yes, positron annihilation can speak a little bit about defect density. Also, annealing effectiveness, precipitation can be recognized, types of the defects. We can study near surface region by positron beam, etc. And finally, people expect that they obtain some product which is useful. Let's speak about the results. The big challenge for the study of irradiated reactor pressure vessel steel is cobalt-60. Therefore, you have to change technique from 2 detector setup to 3 or more detector setup. Or another possibility is to use positron beam. Both approaches are done in the last 20 years. So, if you have the cobalt-16 side, you can reduce volume of the specimen. But finally, you need at least 5 to 5 millimeter specimen to make some measurement. It's not possible to reduce it too much. You can reduce number of the samples, but you need at least 3 points to make some curve. It's also limited. Or application of other techniques if possible. No, it's not possible. You can come back to the appellation. For the cobalt-60, which is disturbed by this 117 and 133 MeV peak, you can use the pulse low energy positron system in Munich. Was my case, but other positron beam is available as well for it. Because you reduce the volume, and in my case I had 20 micrometer in voids. And radioactivity decreased several order. 3 detector setup, yes, it's used for 20 years and in many laboratories. All to wait, but the decay is more than 5 years. And the PhD student needs to finish PhD work in 3 years or in 4 years. And to wait 60 years till the specimens will be available for the measurement, it's not recommended. Good. There is another way to make experimental simulation of irradiation by ion implantation. And you can decide which type, and implantation by hydrogen ions seems to be, from the mechanical point of view, good approach. Protons have a charge, neutrons have no charge. There is difference. Nevertheless, the mass of the neutrons and protons is the same. Therefore, these knockout atoms can be simulated by the implantation of the protons of the hydrogen. Of course, previous speech was about the ODS steel. There is declared 0 cobalt content. It's not true. A small amount is in each steel. So this approach will be perhaps in the future also for the ODS steel. I know that the level of the cobalt in ODS is perhaps 3 orders lower, but it's still there and still disturb the results. Good. There is possibilities what can be studied by positron annihilation. I will focus on evaluation of high implanted versus irradiated nuclear materials, because the idea was not to handle with the real irradiated specimens too much, only for the verification, and all these experimental irradiated, means non-implanted specimens to use as verified original specimen. Our technique, which was used, if you have only implanted specimens with the low energy, up to 10 megaelectron volt, there is no spallation reaction, these specimens are not active, and it's suitable for the measurement by students in the laboratory. So the source and the technique which we have in our positron lab. Good. Results. Comparison in between many reactor pressure vessel steels were published in the past. There is difference mostly in the chromium content. The Russian steels have up to 3% of the chromium in comparison to the, let's say, Western or American steels. On the other hand, there is more nickel in Russian steels, 1 to 1.2, or other differences. Nevertheless, in the results, there is clear difference. If you make tempering, the Western type of steels, you will see the shallowing of the positron lifetime, and this peak is mostly connected to the BCC to FCC change of the structure. Much more interesting are the Russian steels, where is the minimum at approximately 500 or 450 degrees of Celsius, and this increase is connected with the reordering of the structure, and there is the hypothesis which was proved by the transmission electron microscopy about this metal carbide movement. It's not possible to make statement only according to one technique. Therefore, we try to make correlation between mass spectroscopy, hardness, Vicker's measurement, strain stress measurements, and you see that maximal hardness corresponds to the minimum of the lifetime of the defect elements if we consider this holomorphic parameter which combine time and temperature of the treatment. Because we are thinking about treatment during, let's say, 30, 40 years at a different temperature. And this holomorphic parameter enables to do this calculation. Also, we can count the level of the destroying material, concentration of the defects can be calculated. And in case of the presentation of Mr. Naga yesterday, the concentration of the Japanese steel was on the level as 1 to 2 defects per 1 million. In the case of irradiated Russian steels, we go up to 15. We have a little bit higher neutron flux and also fluence. This is important for the industry. Industry believe only sharp PV tests. So, in the past we had irradiated reactor pressure vessel steel, and this plot, all these points were measured. It's not simulation. It's measured by me at Munich somewhere in 2002 by the labs. Each this point was measured, and you see the plateau of the best condition, annealing of most defects by 450 degrees of Celsius. But if we go to the Sharpie tests, it's the proof as well. And if you put this both picture together, it was done recently on the same material as this study before, people in the authority will believe also your positron annihilation results. Big advantage of the positron annihilation is you can see implantation. Look on the material, it's the surface. You implant by accelerator hydrogen inside. You can recognize by temp the bubbles of the defects. It's the hydrogen inside, and you can measure it. And you see on the same position the maximum, and by the elevating temperature you can see that these defects are annealed. So combination of them, there is the picture, and people trust picture, to the graph are the best choice. Good. And the current research, we tried to compare German and Russian steels in 3 stages. Not irradiated, original irradiated by the neutrons, and after that compare these results with similar treated materials, but the treatment was done by the hydrogen implantation. To know these materials, it's necessary to know from the previous research that chromium plays an important role in the formation of small vacancy clusters, and also the size of these defects depends on the chromium content. And the second, it's about the nickel. Nickel retards the depletion of the copper and phosphorus in the matrix. The nickel independent effect could take place through the effect of nickel on the irradiation-induced microvolts. Nickel may segregate on these microvolts and stabilize them, and or it can be controlled their formation through its influence on the microstructure. So the German steels, we were lucky because in Germany different generations of the steels were put in the car reactor in 80s after several years of irradiation put out and studied 30 years ago. So the cobalt 60 degrees was substantial. You can see different level of the alloying elements. Most important are these kappa, because about kappa precipitation we can speak for a long time. The mean lifetime on all these not irradiated specimens is different. And this difference is caused mostly by the kappa content. This one is 0.22 kappa. Kappa is now kept under 0.08% of the weight. It's limit for the new steels. Good. If we make two-component analysis, let's say according to standard rapid model, we have the first component, about 100 could be, and the, let's say, defects component, it's almost stable at this level, let's say 130, 140. Intensity of the defect component is quite high, let's say 30 to 40%. In comparison between reactor pressure vessel steels of these approaches, different chemical composition, we can state it that the Russian steels have perhaps smaller defects, mostly dislocation and monovacancies, in comparison to the German steels where higher these defects lifetime up to 200 picoseconds was appeared. But the concentration of these larger defects in case of the German steel was smaller. 200 picoseconds, it means that there should be some devacancies as well. In case of the Russian steels, it was mostly dislocations and monovacancies. Good. Neutron irradiated steels. These German steels from the Karl reactor were transported in the frame of the project Long Life, and we measure it as subcontractors for Areva company. There is the chemical composition of irradiated, mostly weld metal, Schweißgut in German, weld metal in English. And you see that the content of the kappa was, let's say, limit, and 0.22, which was the highest one from the past. Transport, it was a huge story. We needed 200-liter barrel to transport it from the Belgium to Slovakia. It takes 2 years till the transport was accepted. Finally, the activity was not too high, but important messages. We had original irradiated by neutron irradiated specimens on this level, then top 19 centimeters as well. It means that it's really on the level 0.1, 0.15 dPa as maximum. We measure it by 3 detector setup. There are some results. We see also two-component analysis, and we calculated also concentration of the defects in the material. In this material, B16 weld metal, it was higher than other one. Nevertheless, the not irradiated level was at 1. So in each material at the beginning you have enough defects. Summary. In comparison to not irradiated steels, there was observed some increase in the defect size due to performed neutron treatment. Based on past results, there was cluster format due to irradiation in German steels. It's a very important message, because if we would identify the larger defects like voids, this obstacle and embrittlement would be much higher, and it would be not possible to allow the operation of nuclear power plant anymore. This fact can be interpreted by vacancy type defects. Be hardly any responsibility for radiation induced hardening and embrittlement. So, and the comparison between implantation and neutron irradiation, which was done between these specimens, was we implanted hydrogen by our accelerator at 3 different levels. And we went up to higher implantation dose, but let's consider about this 2 dPa. Also, EVR reactors in 60 years will never achieve 2 dPa. And when we compare these results, not irradiated and implanted, there is as received, irradiated, and 3 different levels of implanted. One material is E370, and we see comparable level if we irradiate and implant by level 2 dPa. The defects are almost the same, so it's proved that defects caused by implantation are very similar to the original irradiated defects. So, to conclusion, the defects in the Russian case were smaller, no large voids. It means these no large voids or vacancy cluster, it's important for the regulatory authority to agree, but decision is not made according to positive annulation. Decision is made according to enzyme notch test and Sharpie tests. It's only additional information. And due to hydrogen implantation, increased defect size to similar values as in neutron irradiated specimens and defects accumulated to the bigger cluster, it is possible way to simulate neutron irradiation under certain circumstances. And that's all from my side. Thank you for your attention.
Yeah, Mado, thank you very much, especially for being perfect in time. Very good. So we have some time for questions, please.
I'm always worried when we take the specimen from the reactor and we give it, so it's very hot, right, in terms of radioactivity. And when we give it to cool down, I'm always worried, do we really, is the defect maybe at near those time, especially if you have the interstitial and isolated vacancies, they can move, right, and they can adhere with time. So do you have any information regarding this? Do you really have? You see any?
Yeah, I think since 30 years, something could happen to your defects.
Yeah. It's at the room temperature, so we do not expect some mobility of the defects, but after 30 years aging, I would agree with you.
But there is mobility also. Special now. I think we can't assume there's no mobility.
Good. What we can do, yes, your question is on the place. Yeah, I fully agree. During 30 years, also the normal aging at the room temperature can play some role and some changes can appear. But what we can do other? First, what we can do is to measure in hot cells immediately after the irradiation. But to make some experience by the distance manipulator is almost impossible. So we can only make it colder. Perhaps the first specimens which I measured were after 2 years from putting out of the reactor. But it was these thin foils, 20 micrometers, they were still active. And we had in the positron beam, the ratio peak to the background on the level only 5. In other measurement, it was 10,000. You lose something by the measurement of the cobalt containing radioactive specimens. That's true.
Okay, any more questions? Yeah, one more question.
For the neutron irradiated steel, you mentioned that 1-2 vacancy maybe not contribute to brittlement of the steel. You mentioned that. Can you explain? Because you also mentioned that the density of the 1-2 vacancy also is very large, but it not affect. It didn't affect the mechanical properties. I don't know. You explain?
I tried. In 20 years, we measured hundreds of the different treated specimens of the reactive pressure versus steel. We never found something which could be as the large defect after irradiation. Every time it was on the level 160, 180, perhaps up to 200 picosecond. And unfortunately, I mentioned it some years ago, perhaps 15 years ago, in one conference, ICPA, the big progress would be if we would have the time resolution on the 10 or 20 picosecond. It's not the case. So we can hardly distinguish between dislocation, screw dislocation 150, edge dislocation 175, monovacancy in the steel or in the iron 165, divacancy 175. It's very hard to distinguish in between defects or some misfits on the grain boundaries also on this level. So we have agglomeration of possible defects, and other consideration can be done by the transmission electron-microscopy results or other techniques. Nevertheless, if you have only this level of the, let's say, defects positron lifetime on level 160 and not 300 or not 250, you can quite sure say there is no big voids and big defects in the material. That's our explanation.
Yeah, so thank you very much. Time is over. I would like to thank Vlad once again, and there is, of course, your present from